let's go forward.
Hello, Ian.
Yes.
Hello.
Yes, hello.
Can you please again explain this density compensation in VSI and IVSI? There are two ceramic types.
I'll just finish off with Sanjay first, okay?
Okay.
You just listening.
Okay.
Now, the next one is we call a calibrated altitude. Okay, we have now calibrated the instrument and we have taken into account any errors. So now the pilot knows if he's flying, if he's indicating 2,000 feet, he's actually at 2,010 feet. So he can adjust his altitude or what the altimeter is reading to give him the exact altimeter. So if he's over reading by 10 feet, he knows he has to fly 10 feet less to get the correct altitude. Okay, so calibrated altitude, as it says there, is adjusted for instrument and pressure error. So the inaccuracies, not having the calibration sheet, is my instrument inaccuracy. And the other thing was we said pressure error. And pressure error is aircraft maintenance engineers, we can't do anything about. Pressure error is designed out of the system by the designer of the aircraft. They'll put the aircraft in all the wind tunnels and they will adjust the static vents, the static ports for any errors caused by the turbulence of the airframe. Okay, are you happy with that, Sanjeev?
I'm happy.
Good. And Chris, what was it you wanted to see? Chris?
Yeah.
What was it you wanted to go through again?
No. I have some other questions.
Okay, on you go.
This warning flag and the crosshatch, are they similar or what?
With regards to what?
No, the warning flag is when the power failure it comes. The warning flag.
Right. So we're talking about the VSI. Yep. The IVSI. Okay. Right. A warning flag.
Yeah.
Now, if I'm flying in straight and level flight, okay, if I'm flying in straight and level flight and I have an electrically operated instrument and either say internally we have a short circuit or the power supply to that electrical instrument fails.
Yeah.
How does the pilot know that his instrument's no longer working? Okay, and that's why we have a warning flag. And usually what will happen is it's a little solenoid operated. So when there's power, the little off flag is pulled up from the front of the instrument. And when the power fails, it will drop down. Okay, we will be looking at the off flag system a bit more in depth sometime today. Okay, but basically the off flag, when you lose power to an electrical system, and this is the exact same for any electrical gauge, when you lose power to the gauge, either it's switched off or there's a power failure, the little off flag will drop down into the front of the gauge, indicating to the pilot that the system has failed. Okay?
Yeah.
After that, Chris?
Yeah, and this in altimeter, simple altimeter, we have below 10,000 feet the crosshatch flag.
Yes.
So how to know that it is this power failure flag or the crosshatch?
No, that in this there's no power in the simple altimeter. All that happens mechanically when it gets to 10,000 feet, as the pointer comes round, it just grabs a linkage and pulls the shutter.
Yeah.
Okay. Across the crosshatch, indicating he's over 10,000 feet. So it's all done mechanically.
Okay.
Okay. In a simple sensitive altimeter, unless there's any electrical lighting in it, there is no electrical power to a simple sensitive altimeter.
Yeah.
Okay.
Thank you.
Anyone else got any questions you want to go through?
Yes.
Who was that?
This is Chris only. I have one more question.
Okay, Chris.
This if static is blocked in ASI. Yesterday you had told, but I got confused. That's why. Will you please explain that?
Okay. We're not going to. There is no requirement to do major faults in this module. But what if you said static was blocked, okay?
Yeah.
If static was blocked, let's go into. Okay, we'll look at this little picture here.
Okay.
Okay. Oops, turn it around the right way. So now we'll look at the back here. Okay. So
yeah.
Here's my airspeed indicator. Remember, we said it has two inputs. We have static and pitot. You happy with that, Chris?
Yeah.
And we know pitot equals dynamic, the forward speed plus
static.
Oops. Yep.
Yeah.
Now, we did say, oops, let me draw this again somewhere. So pitot equals dynamic plus static. Yep. So that bit there, that's the capsule. And we put static to the case. Okay, so that opposes the static. So we've got that. That's basically how my little formula looks. Yep. Yeah. And you said I block the static line. Agreed?
Yeah.
Right. So let's have a look. We'll just do this now. Give two values. Okay. Oh, can someone just turn the microphone off? So if I give my dynamic speed 100, I give my static pressure 10. Yep. And my static pressure going to the case of 10. I have a dynamic, my pitot pressure is 100, okay? Or my speed will be 100. Agree with that? Now I block the static vent. If I block the static vent, I no longer have any static going into the case. So now my total is 100 plus 10 minus nothing. Therefore, it would be 110. So if I ever was to block the static port, my instrument would always overread. Okay?
Yeah.
Okay? That's how we improve it mathematically. Yep. Who else wanted a question?
Yes, Lynn, I have a couple of questions.
Okay. Yep.
First one is actually yesterday I didn't convince regarding this VSI temperature compensation by the laminated rod.
Yes.
Can you please let me elaborate about this? Because laminated is only, as per my opinion, in the book I saw, there is only laminated for ASI, not for VSI. So
no, it's also for VSI. No. Hold on. VSI. Okay. Right. So. Right. VSI. If you actually look in your notes. Where are we? Let's go get notes. So if you go into the VSI, okay, you've got it. It's just after when we talk about the density compensation. There should be a little paragraph saying temperature compensation. Did you see that?
Density compensation?
No, it's just after it, a couple of pages after it. It says temperature compensation.
Yes, there is.
Right? And if it says there, as with these other instruments, the ranging bar is bimetallic of inverse steel and brass, okay, to compensate. So
Yes.
as it says in the notes, the temperature compensation is done by an inverse steel, a bimetallic inverse steel laminated ranging bar.
Is it the same as laminated?
Yeah, it's a ranging bar. Basically, it's going to be layers of.
So can
The
it? So is
one
it
layer of inverse steel, one layer of brass, okay, and it'll allow it to bend. Okay.
So means so ASI in the BSI the same?
Exactly the same principle. Okay. The
Okay.
temperature compensation is done by a laminated inverse steel ranging bar.
To both ASI and BSI, right?
Yes, correct.
Okay, thank you. And one more is
Yes.
regarding this case leak regarding this same topic BSI. What happens if the case leak and this capsule leak is the same? It will read the level flight.
Static will be basically changed. It would depend on the size of the leak. Okay, that's quite a complex case. You're not going to be asked that in this exam. Remember, this is basic. Okay, right. So it would actually depend on the size of the leak. I know I'm maybe not answering your question directly, but you can see here. Remember, in the case, it's a calibrated leak. It's a metered leak of a known quantity of air. So if I have another leak somewhere, let's say I had a leak here, okay, a small crack in the case, as it changes height, air's going to get in, so it would make it inaccurate, okay? That's the best answer I could give. You'd have to do, specifically, you would have to do further leak checks on the instrument. But what you could do, okay, I was going to talk about this morning. Let's get rid of that. Imagine now, okay, imagine now that this here is it's either usually rubber or a bit of metal piping inside the case. If that was to break, okay, so that pipeline here was to break. What could we say? What could we say? Well, if this rubber pipeline between the pipeline and the capsule was to break, if I changed height, would the pressure change in the case and the capsule at the same time? Hello?
It will compress, right?
No, think about it. If I break the pipeline, remember everything inside the blue line is inside the case. If I break this pipeline here, okay, I break that pipeline. Any air coming in, okay, any air coming in would go straight into the capsule, but also would go straight into the case. Would I have any pressure differential?
Okay.
So if I don't have any pressure differential, so if I have an internal breakage, I could actually say nothing will change because I have no pressure difference. Does that answer your question? A leak on the case is very difficult to give you a precise answer, but a breakage, a complete breakage or a leak inside the case and the pipeline, there'll be no pressure differential. So if the aircraft climbed or descended, I would get no indication of a climb or descent. Okay?
It will indicate level flight.
Does it make any difference? If the aircraft starts to go up, or what? No, rephrase that. The aircraft starts to come down. we know the pressure is going to go up. Agreed with that? Yeah?
Yeah, yeah.
So if the aircraft starts to go down, pressure is going to go, atmospheric pressure is going to go up. Yeah? So now the air pressure is going to come in through the static pipeline. It's going to come to this point here. This point here is broken. So if that's broken, the pressure in the case must equal the pressure in the capsule. If there's no pressure differential, with no pressure difference, the gauge will indicate 0.
Okay.
Okay? You happy with that?
Yes.
Okay.
Exactly. It's in the case of is the pipe which totally broken, right?
If it's broke, yes.
In
There's
the
no
case
way
of
we can have.
capsule,
Basically, if it's broke, we're no longer using this calibrated leak, are we? To make a pressure difference. So the pressure in the case and the capsule will be the same. The pressure is the same. There's no difference in pressure, therefore there's no indication. It will stay at level.
Okay, is the same case for the capsule leak as well?
Yeah, if it breaks if it breaks here,
yeah,
the pressure is going to go straight into the case, isn't it? So basically, it would be the exact same. Yep. Does that answer your question?
Okay, thank you, Len.
Okay. Anyone else want to do anything else before we start this morning?
Thank you.
Ian, density, can you please explain again this BSI, IBSI density compensation, this ceramic type and capillary hole orifice type?
Okay. Right, the first thing is about density. We know density, the higher I go up, the less molecules I've got air, the air is less dense. And remember I said all my instruments are designed to work at sea level with 1013.25 and a set density at the sea level. So for my VSI to give me a very accurate change in height, because remember if I go up and down, the density of the air is also going to change. So less molecules are going to go into the capsule, therefore it might not expand or contract at the right amount. So we have two types, okay? We've got two types, ceramic type and capillary and hole, okay?
Okay.
We'll just have a quick look at this one here. So now this is actually, all this bit here is actually inside, it's inside this is inside the case. Now, we know we can't measure density in aircraft, but we can say density and temperature are directly related. So if I go up in the atmosphere, the density of the air goes down, but we also know the temperature goes down. So we're going to use temperature as a measure or an indication of the density of the air. Okay, some very clever people have worked this out, more clever than me and you. But what we can say, look at this diagram here. This temperature density compensation is going to be carried out with this bimetallic strip, which is attached to a little plunger, okay, which basically will allow some of the outside air to escape. So what we want to make sure is in the case, the density is always the same. So how do we do it? Let's imagine now I'm going up in altitude. We also know that density is going to go down and temperature is also going to go down. So what happens with this bimetallic strip? I need to make more of the air go into the case. So what happens here, as it gets colder, the bimetallic strip starts to bend in. The plunger starts to seal the little vent, which allows more of the outside air to go into the case. As I start to come down, okay, we know density is going to go up and temperature is going to go up. And if I come down far enough, the density of the air will become quite dense. So what we're going to do is the temperature goes up, we'll make the bimetallic strip open a bit. I'll open the plunger and allow some of the air to escape. So we're going to keep the same density. Okay, so that's big. So what you need to know is in a ceramic type metering unit, how does it work? It basically works on that relationship between density and temperature. And it's controlled by the bimetallic strips, which opens and closes with the temperature, which is related to the density. So you might be asked, how do we control the density in a vertical speed indicator with a ceramic type? It would be basically the bimetallic strip opening and closing the port. If you were asked in a ceramic type metering unit, what would happen if the density aircraft started to go down? Well, we now know density is going to go up, temperature is going to go up, so we're going to open and release some of that air. Okay, are you happy on the ceramic type?
Yes, Jim. Yes, okay. I am happy.
Good. The next one is called capillary and hole. Okay, It's just another bit. You'll find this in the more basic aircraft. Okay, there's no moving parts to start with, and all it relies on is it says there a combination of holes and turbulent airflow. So on here, if I have more, as I said yesterday, the shape of it is like this. So this little orifice is this shaped like this. Okay, so that's the little device, and that's actually in a in a pipeline that goes like this. So in this part here, in the case, which is here, I want to make sure again I get the correct density of air. So imagine I now get lots and lots of density, okay? Get lots and lots of very thin laminations of air. So we've got lots and lots and lots and lots and lots of layers of air. As it starts to get, this air starts to get forced through, it starts to become, gets caught in here and becomes,
turbulent.
It becomes more turbulent. And as it becomes more turbulent, we now know turbulent air has less pressure. So the time it gets to here, that sort of forces in like this. Time it gets to here, we've actually gone to, let's say, the basic 3 laminations of air. So when I've got high density air, the turbulence causes it, the orifice, they call it the holes, but it's little sort of like the top of a castle, these sort of squares, indents, because turbulence causes a pressure drop. A pressure drop means we've got less pressure, less dense air. Okay? Does that answer your question?
Okay, and
Yep. So basically, lots of dense air, when it comes in, it becomes turbulent. Turbulent, we don't have a pressure drop. Pressure drop means that the air is not as compressed, therefore it's less dense. Okay, that answers your question.
okay, and thank
Okay,
you.
lovely. Okay, good. Everyone else happy? Well, happy as you can be on a Friday. Oh, somebody ask a question?
No, Lynn.
Okay. Now, I've given you some questions here. If anyone later on today wants to ask any of the, if you've went through the questions, good. Again, you've probably got some of this weekend, maybe more time to do it the weekend. Again, if you get any questions, give me a shout. Okay. I can't guarantee, but again, on Monday, or if you want to email me, if you get any questions, you've got my email address, or what's email address. If you get any questions over the weekend, put them in. At least on Monday, I can have prepared answers for you. Okay? Right, so that's the pitot-static side of basic instruments carried out. So basically, that's instruments going to give me my speed, my height, and my rate of change of height. Okay, so now we need to look at, one of the things we're going to look at is direction. Okay, navigation. Okay, navigation. And two things about navigation is, yes, my direction, but also if I'm level, because if I'm rolling, okay, my wings aren't level. It basically means I'm going to bank and I'm going to end up crashing into the ground. If my nose is up and I keep going up, 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 I'll end up, I'll stall and I'll crash. If my nose is down, I'll crash. Okay, that's not a problem if it's a lovely summer's day. Okay, and the pilot can see the ground. But if he's flying at night, or in cloud, or in fog, he has no visual reference. Okay, he has no visual reference to tell him whether his wings are level or his nose are up or down. So the next sort of instruments we're going to use are all gyro controlled instruments. Okay, and I've got, you've all done physics, haven't you? You've done the physics?
Yes.
You all know about, most of you know about gyros. Okay, we're going to talk about 3 gyros in the next day or so. But I'll break the 2 gyros down, the 2 main ones. We have a vertical gyro, and when I mean the vertical is the, hold on, is the axis of spin. Okay, the axis of spin. Okay, so that's my axis. And if I was to say that's the ground, okay, you can see it's vertical. Okay, the axis of spin is vertical. So the axis of spin is vertical, and here's the rotor of the gyro. And that's going to give me, if you look at it, the first thing a vertical gyro can give me is roll. And if I turn it round the other way, is pitch. So a vertical gyro gives me pitch and roll info. Okay, so it gives me pitch and roll information relative to the Earth's surface, and we'll look at how we do that. The next one is called a horizontal gyro, and the axis of spin so my axis of spin is horizontal to the Earth's surface. So now my rotor of the gyro is like that. Okay, oops. And what that does, a horizontal gyro gives me direction. Okay, gives me direction. Right, so we're just going to do a quick recap on basic principles of gyro. Okay, just so we get this understand for the next bit. So now I have an axis of spin. Okay, that's the axis, and there's the rotor of my gyro, and that's spinning round. Okay, and the gyro has two features. The first one is rigidity. Okay, rigidity, and that's dependent on the mass of the rotor, the speed of the rotor, and the diameter. Okay. And what rigidity does, without any outside influence in a perfect gyro, okay, a perfect gyro is, once I speed up a gyro, get the rotor going fast, it will always point in the same direction okay, in space. Okay, that's the official term. Okay, that gyro, once I speed it up to its operational speed, if it's a perfect gyro, that axis will always point in that direction. Okay, will always point in that direction, unless an external force is applied. Okay, an external force, and one of those forces could be friction of the bearings, wind, vibration. Okay, and when we start to apply a force, we get something called precession. Okay, and what happens is, when we get precession, the gyro's axis starts to move. Okay, starts to move. The term we use is wander or topple. There's two types, there's wander and topple, but basically it's moving away from its either vertical or horizontal axis. Okay, and precession always happens, okay, 90 degrees ahead of direction of rotation of the rotor. What does that mean? Okay, so let's have a quick look at that. So I'm going to look down onto the rotor of my gyro. Okay, and there's my axis in the middle. Okay, so what this means, if I put a force at that point there, okay, I put a point at that point there, the force doesn't do anything at this point. The force is felt and acts 90 degrees. So if I do that, you can see that's 90 degrees. So if I put a force here, rather than it going tipping there, it now tips. So the force is going to push the rotor down at this point here. Okay, so we've got to understand these two laws of gyro's rigidity. Makes the gyro constantly want to point in the same direction in space. And that happens with a perfect gyro. But we'll never ever get a perfect gyro because friction is a force. And we can never get bearings to be completely frictionless. So any force, friction, vibration, touch, wind will cause precession. And precession always acts 90 degrees ahead in the direction of the rotor. So basically there's a rotation of that rotor. The force physically is felt there, but doesn't do anything until 90 degrees. So I want to push it, I push it down there, but it doesn't actually move. The rotor doesn't move until there, so it's 90 degrees. Okay, are we happy with those two basic understandings of the laws of gyros? Okay, we all happy with that, gentlemen? Yes? Some of you have probably done it before. Yeah, okay. Just a refresh because we need to talk about that because we need to talk about gyros most of the day. Okay, we talk about gyros most of the day. Oh, we're going for it. Right. Oh, come on. Let's get this up. Come on. Give me a break. That's better. Right. So the first indicator we're going to talk about is called an artificial horizon, okay? Sometimes known as an ADI, airborne direction indicator. It is a vertical gyro, okay? So the first thing we say about an artificial horizon, okay, it is a vertical gyro. So you want to make a little note in your notes. So basically that is a, nope. So vertical gyro, so it's going to detect changes in pitch and roll, okay? It's going to detect changes in pitch and roll. So basically it's going to tell the pilot whether his wings are level or his nose is either up or down, okay? It's a very important instrument for the pilot when they're doing instrument flying. Because basically it's the only reference he has to the Earth's surface is this instrument. So when he's in cloud, when he's in nighttime, or is in fog, this is the only instrument that will tell him whether his wings are level or his nose is up or down. Okay. Oh. Believe it or not, gentlemen, we've been going nearly an hour now. Well, for you anyway. We'll go for a 15-minute break. We'll come back and we will get on with actually how the thing works. Okay. Any questions what we've done so far this morning about gyros? No? Okay. We'll go for a quick 15-minute break. We'll come back and we'll get on with it. Okay?
Okay.
Okay, lovely. So what's it like in Kathmandu today? What's the weather like?
It's little bit cold, windy, and raining. Slight rain.
Yeah, it's heavy rain here. It's been raining for about 4 days now.
Here, slight rain, windy.
Yeah. Further north from here, just about 40 miles away, the snow is really, really, really bad.
A very nice helicopter.
Yeah. Proper aircraft or helicopters.
Yeah, I also work in helicopter.
Yeah, well, as I keep saying, all the best aircraft engineers work in helicopters, rotary wing. I took a this when I worked in Norway. So we're ready to come and pick up a load.
Yeah, this cargo sling load, right?
Yeah.
Okay. We also do the cargo sling, but not human long line rescue.
No. No, those aircraft could do the lot. Okay. Unfortunately, they're long gone now. They're all retired. Not many countries using them now.
And in?
Yes.
I have a question.
Okay.
The logarithmic division of pointer in VSI.
Yes.
So what does that mean? It is written that for small, large, something is there. I have to check.
Yeah, a small amount of movement gives you a large output.
Yeah, larger division at lower values and smaller division at higher values. So what is this?
Right, okay, let's go back.
I don't understand this.
No problem.
It's about confusing. Larger division at lower value, smaller division at higher values.
Right. So basically, it's all down to something called square law. Okay.
Yeah.
Okay.
Yeah.
Yes, square law. Now, if we look at that little statement, it says as speed doubles, pressure increases by 4. Okay. So what we need to do is to take into account that, because it's not directly proportional. It's what we directly proportional will be one knot in, 1 psi up. Okay, this will be like 1 knot in, 1 knot out. Then it'll be 2 knots in, 3 knots out. 3 knots in, 5. 4, 10. 5, 15. 6, 23. So basically, it's not what we call the scale is. Oops, no, that's bad. I'll draw up here. The scale is not what we call directly proportional. It is. Oh, God. Try to draw on a computer, it's a nightmare. It's like that. It's logarithmic. Okay. So what it says in here, if we look here. At the beginning, small change, small put in. Where are we? You can see here, small change. Okay, small input, small change. Move it up and go the same amount. Okay, so if I have to move it the same amount, so that's 1, that's now 2. You can see now, it increases. If I now do another 1, make that 3, you can see now the amount of change. So for the same amount in, you can see now I'm getting more out. The change is getting bigger. Okay, can you see that? I know it's a bad drawing, but can you see what I'm getting at? Hello?
Yeah, I can see you.
Right. So now what we need to do, we can't change that law. That's a law of physics. We can't change it. We just have to compensate for it. So just imagine now, okay, this is the ranging bar. So I have a small movement. If you can see here, it's right in the middle. So any small movement will get the correct amount. It will move the same amount. But now, as I start to increase speed, okay, what I want to do is, for the same amount of movement, if I see if I can draw it, very difficult on this computer. There's my banana slot, okay? So at zero, it's the bottom. So now I move it, let's call it, we'll change it by one amount. That's how much the pointer's going to move, okay? Now, if I was to change it, oh, come on, give me a chance. Now, if I change it by the second amount, oh, come on, give me a break. The second amount, the curve, okay? The curve is hopefully keeping the amount of movement of the pointer the same. So even now, you can see here I've only moved, so one bit was only a small angle. The two movements, the two parts, I've got a bigger difference, and then I do it for the third time, the third amount. You can see that the actual movement, even though now the angle, okay, of the angle of the input has increased. Because of that banana slot, the curve in the banana slot, you can see the amount of movement it would produce on the pointer would be equal.
Okay.
Okay, so that's what we're doing, is trying to take out that curved output, okay, to make the scale be even all the way around. Okay, Chris?
Yeah.
That's all it's to do with, okay?
So to compensate this, the banana slot is there.
Yeah, to compensate for square law. That's all you have to remember.
Yeah, okay.
It's very difficult. Remember, ladies and gents, when you're dealing with multiple choice questions, it's very difficult to ask the complete operation of a system. Okay? But you can see there why it is. Okay, let's go back into put a point.
Thank you.
No problem.
And how you are able to change this background?
Yes, I am, yeah.
Yes,
only recently. I'll change it every day or so.
Okay.
Okay.
Yeah. It looks nice.
My last one was a picture in Mauritius. That's a lovely place. If you ever get a chance, Mauritius, beautiful place.
Yeah.
Okay. So now we're going to look at the artificial horizon, also known as the ADI, Airborne Direction Indicator. It's a gyro instrument, okay? And the first thing we need to think about is in there. So in the back of this instrument is a gyro. If you actually look at this bit, it's called what we call the gull's wings. This is basic. This part, these gull's wings are actually attached to the aircraft. So what actually happened is the case is attached to the aircraft. And remember I said the gyro will always want to point in the same direction in space. So the gyro, its axis will all be vertical, so now the aircraft moves around it. So the center part when I roll stays the same, and it's actually the case that moves. We'll look at this a bit more in depth in a minute. Look at the ADI, the attitude indicator. So there's the gull wings. That gives you the level, the wings of the aircraft. And it's broken into two parts. We have a brown bit and a blue bit. Some we've got a light blue and a black. It's the same thing. One's sky, one's ground. Okay. You can see there's the sky and there's the ground. And it also gives you your angle and pitch. So in the centre there, you can see it's got 5 degrees, 10 degrees, 15 degrees, 20 degrees. That's pitch. And then we have, on the case itself, we have the roll pointer. 10, 20, 30, 45, 90. If you look at the gull's wings, okay? If you look at the gull's wings, in this particular picture, the gull's wings are below the horizon. There's a horizon in the middle. If the gull's wings are below the horizon, it means the aircraft is going down. Okay, the wings are going down. If the gull's wings were above the horizon, the aircraft would be climbing. So in this case, it's approximately descending at about 10 degrees. 10 degrees nose down. Right, how it works inside. How it works inside. Okay. So how it works inside. You can see there's my axis. Okay. We can see here, there's my axis, and it's vertical. And you can see now that the gyro is spinning. Okay, so it's spinning in that direction. In a gyro, okay, we're going to look at these here. The frame, what contains the rotor, is something called gimbals, okay? G-I-M-B-E-L-S, okay? Gimbals, the frames. This one here is the inner. This one here is called the outer. And you can see now the inner gimbal is connected, is basically supporting the axis of the rotor, okay? The axis of the rotor. So now the inner gimbal is attached to the rotor. It will always stay vertical, okay? It will always stay vertical. The next thing we need to look at is the outer gimbal. And if you look at the outer gimbal, it has again this sort of C slot. And but coming through that C slot is a pin, okay? A pin coming from the inner gimbal, okay? And that pin is called the actuate. That's called the actuating pin. Without this pin, this wouldn't work. This gyro, or it would give the pilot, when he was climbing, it would tell him he's descending. There's the horizon bar. That's the roll pointer. And that's your gull's wings, okay? The gyro, that bit there is connected to the case. So this end here, that's connected to the case, which is attached to the aircraft. So the first thing we always need to remember, in a vertical gyro, the axis will always continue to point in the same direction. So let's have a look at how it operates. Okay, how it operates. Now remember, the pilot is sitting here. So he's looking at the instrument, and you can see here, that's the front of the aircraft, the forward, looking forward. So that's basically, so that end here is the cockpit. That's the nose of the aircraft. So what we want to do now is we want to say the aircraft climb. Okay, so the aircraft's going to go up. That means because this is attached to the aircraft, this bit goes up, okay? This bit goes up, but the inner gimbal doesn't move, okay? The inner gimbal doesn't move. Now let's have a look at what happens here. The horizon bar is pivoted at the front end of the outer gimbal. So now that also wants to go up. Now this is where this actuating pin comes in. The actuating pin, basically what it does, it changes the fulcrum point, okay, changes the fulcrum point of the horizon bar. Rather than going up, it's going to push it down. So look, that goes up. This part is going up, but this, the inner gimbal, isn't changing. So what happens is that starts to go up. This, as the horizon bar, this end starts to go up. This end starts to go up, and what it's doing, it forces the actuating pin. Well, it looks like it's going down the slot, and as it goes down the slot, it pushes the horizon bar down below the gull's wings, indicating a climb. Okay, the wings are above the horizon bar. It indicates a climb. Okay, so a couple of things to take out of this. The inner gimbal, when the aircraft either climbs or descends, doesn't move. Okay, it's only the outer gimbal it's physically getting tipped up on its end. If it wasn't for the actuating pin, we would end up with the horizon bar above the wings. So what causes this horizon bar to work or give the pilot the correct indication is this actuating pin, okay? And all you need to remember about the actuating pin, it changes the fulcrum point of the horizon bar, okay? As the aircraft climbs, it will put the horizon bar down. If the aircraft goes down, it will push the horizon bar up, okay? That's the basics on that, okay? So remember, a couple of things to remember. The gyro is a vertical gyro, which means it wants to keep pointing vertically. When the aircraft either climbs or descends, the gyro and the inner gimbal stay pointing in the same direction. They don't move. The front of the outer gimbal is the place it's going to move. Okay, is the place it's going to move. As we said there, it goes up. That goes up. It also, because this actuating pin is attached to the inner gimbal, that actuating pin doesn't move. So as that goes up, it looks like the actuating pin is getting moved along that slot. So it pushes it down. So basically it's going to push the horizon bar down. Okay, horizon bar down. Oh. Now if the aircraft starts to go down, the front of the outer gimbal goes down, the front of the horizon bar goes down, the inner gimbal doesn't change. Inner gimbal doesn't change. So as that's now getting pushed down, it makes it look like the actuating pin is there. Okay, makes like the actuating pin is there. So now what happens is the horizon bar goes up, okay, which means it goes above the gull's wings, giving it an indication of a descent, okay, giving an indication of a descent, okay. Are we all happy on the operation of a vertical gyro in an artificial horizon? And are we all happy with the purpose of the actuating pin? Anyone got any questions on it?
It's okay, sir.
Okay, good. Right, let's look at some roll. Okay, we'll now look at roll. Now, if the aircraft starts to roll, okay, now at the end here, when we said it's connected to the case, but there's a bearing there, okay, there's two bearings there. So now as the aircraft starts to roll, remember we said the gyro wants to keep pointing the same direction in space, i.e. vertically, straight up. So now as the aircraft rolls, look what happens. It will roll. Oh. Let's say it rolls to the right, okay? The gyro stays where it is. So the inner gimbal and the outer gimbal don't move. The inner gimbal and the outer gimbal don't move. And what happens is, this pointer, okay, as the frame starts to move, the pointer is going to go that direction, okay? And if you look here, this little arrow at the bottom has moved to the right.
Excuse me, sir.
Yes.
Excuse me. Can you make your cursor quite big? Cursor.
Say that again, please.
Your cursor, sir. Mouse cursor.
Well, okay, I'll see what I can.
Yeah,
I'm just drawing at the moment. Okay. So that's that pointer. So what's happened here is it's indicating, so that's the aircraft's moved this direction, but this bit here hasn't moved. It's only the case which is attached to the aircraft has moved, indicating a roll to the right. So when we do roll indication, okay, the actual inner outer gimbal doesn't move. It's only the case which is attached to the aircraft it moves, okay? And that's how we get the roll indication. Okay, are we all happy on that, or do you want me to go through it again?
Once more, sir.
Once more, okay?
Yeah.
Is that pitch and roll or just roll?
Just roll.
Just roll.
Okay, just roll. Right, lovely. So, remember we said, here's the pilot. So now the aircraft, let's say it now rolls to the right. Now, aircraft rolls to the right. Here and here we have bearings. Yep. As the aircraft rolls to the right, we have to go back to the principles of gyro. Remember, the vertical gyro, that axis keeps wanting to point vertical, and so basically vertical upwards. Now, as the aircraft turns, this doesn't want to move, and this doesn't move. The aircraft rolls round the gyro. So now looking what happens here, this pointer here, okay, doesn't move. This scale is attached to the case of the instrument. So what happens now, that also moves to the the right. So you can see that this scale would move round to like this, okay, indicating that the aircraft has rolled to the right, okay. That's what happens. So basically, in roll, the inner and outer gimbal don't move. The aircraft moves round the vertical gyro, okay. So there's not many things we can ask, but how about what happens, okay, when the aircraft, what happens to the gimbals and an attitude indicator when the aircraft rolls? A, do they move to the left? B, do they move to the right? C, do they not move? They don't move. The aircraft rolls round the gyro, okay? All happy in that. Anyone get any questions on it? Okay, good.
Lynn,
Yes.
just you mean to say that in the roll, there is no movement of this external and internal gyro and also the pointer?
Yeah, basically that stays the same. The case, see the roll pointer, see that pointer, okay?
Yeah.
That stays with the gyro and the case moves round. So basically in roll, okay, when the aircraft rolls, let's say to the right, this pointer, okay, this pointer doesn't move. But what happens is this scale, because it's attached to the scale, this scale here, because that's attached to the case, it, oh, come on, give me a break. The scale rolls to the right. Okay, so this part here will now be there, indicating a roll to the right, but the gyro hasn't moved. Okay, does that answer your question?
This case, what caused the case move?
The case doesn't move, the case stays with the aircraft. So when the aircraft rolls, okay, the case rolls with the aircraft. The gyro stays where it is.
Okay.
Okay, that's what works on roll. So basically, the inner and outer gimbal in roll don't move. It's just the case it moves with the aircraft to give the roll indication. Okay, now that's rigidity working well. Okay, that's rigidity working well. But as I said, okay, so we're actually using rigidity there. I've also said that friction will cause the gyro to precess. Okay, and this type of thing, it's going to what's called topple. It'll start to move away from the vertical axis. If the artificial horizon or the vertical gyro moves away from the moves away from the vertical, okay, so vertical to the Earth's surface, and the pilot climbs or descends, is it going to give him a wrong indication of pitch or roll? It will do. So imagine my gyro, it starts to topple or tilt, and my axis is like that. Okay, so what we'd have here is we'd have an indication in pitch, even though I was in straight and level flight. And if I was flying in cloud and my aircraft said it was nose down, the pilot would try and pull the aircraft up, and eventually we'd go into a stall. So we need to make sure that the gyro, a vertical gyro, its axis is always 90 degrees or perpendicular to the Earth's surface. So we're going to use the Earth as the reference for the gyro. So how do we do that? What's common anywhere in the Earth's surface? Gravity. Yeah? Gravity. So if we can use gravity to make sure that the axis is vertical, we'll always have the reference of the aircraft's attitude relative to the Earth's surface, okay? And that's what we call Earth tying a gyro. We're tying the gyro's axis to the Earth's surface. So we always want that gyro axis to be 90 degrees to the Earth's surface. So how do we do it? We're going to precess the gyro, okay? We're going to precess the gyro. There's several ways we can do it, okay? There is several ways, but we're basically going to look at the electrical side, okay? We're going to look at how we do it electrically. So what we're going to do, I'm just going to go on a page or two. Is what we're going to do is we're going to put some little torque motors, and we're going to put them on the axes between basically the gimbals. Okay, so we're going to put little torque motors. Right, so what we need to do is look at gravity. Okay, look at gravity. And what we're going to use is called electrolytic switches. So looking at this one here. Now I'm going to say when the axis is vertical, I'll just go on a page. Oops. You can see here that the tilt switches are on the inner gimbal. Okay, the tilt switches are on the inner gimbal. So now if the pitch starts to come down, you can see this electrolytic switch, the gravity will pull it to one end. And we'll look at what happens. So in straight and level flight, the electrolyte is in the middle contact. We'll look at how this works in a second. So now, if I have it here, if I look here in straight and level flight, if I have .28 volt supply here, and that there is connected to my little torque motor, as you can see, the electrolyte, which is a conducting fluid, there is no path to the motor. The motor doesn't produce a force, and if I don't produce a force, I can't precess my gyro. So let's look at the one above. Okay, let's look at the input above. So now I've still got 28 volts here. Now the gyro starts to move away from vertical. As it moves away from vertical, this electrolyte spreads out. And you can now see here, I have an input, and it will start to go to the torque motor, which will produce a force. Okay, that force will start to precess the gyro. Okay, that force will precess the gyro. Remember the phrase 90 degrees ahead of the direction of rotation. These motors are DC motors, okay? And the direction of the torque is determined by the direction of the current going through the motor. So in this case, the positive side is coming through here, and that will cause the motor to turn in one direction. Okay, if it was to tilt the other way, okay, if the electrolyte was to tilt the other way, we now get the input, it would come through here, through here, through here. I now have the positive side coming in that way, and the motor would tilt, cause the precession in the opposite direction. Okay, in the opposite direction. So this is what we call a leveling system. It's an electrolytic leveling system. The sensors are electrolytic switches. Okay, years ago they used to be mercury switches. That's dangerous. And they will precess the gyro always back to the vertical position. Okay, always back to the vertical position. Okay. Now, so I want to keep that axis there vertical at all times. So what we're going to have is my electrolytic switches. Okay, one will be in the pitch axis and one will be in the roll axis, just like that. So when we're talking about electrolytic switches, why do we have them? To precess the gyro back to its vertical position. Okay, precess the gyro to make its axis back to the vertical position. How do we do that? We use electrolytic switches. How do we determine the direction of the movement of that little torque motor? It's determined by the direction of the current going through the torque motor. Okay, the direction is determined by the current going through the torque motor. It will then precess the gyro back to its original position. And when it's back to being level again, you can see down here, once it's level and the axis is vertical again, the electrolyte is in the middle. There's no path for the current to flow, and the torque motors stop precessing the gyro. Okay. And I said we've got one for pitch, one for roll. And this is for a very basic gyro. More complex ones will have more complex electrolytic switches. So let's look at this, what we call erection system. We'll just start with this one here. That's the roll. Here's my 28 volt supply. Now let's look what happens. It comes in, okay? And let's say it's tilted forward. So this little bead has moved forward. So now we've got a supply down through here. To here. And as it says there, okay, that's on the roll axis, but we were talking about pitch. But look here, the pitch torque motor is on the roll axis, which basically means the roll torque motor is on the pitch axis. Why is that? Remember what I said about precessional forces? Acts 90 degrees ahead of the direction of rotor. So now if I look at my here, so we said we had there's my direction of rotation. Oh, come on. Okay, there's my direction of rotation. So now my pitch, okay, my pitch torque motor, remember my pitch, my pitch sensor, my pitch electrolytic switch sees that the aircraft the gyro has moved or toppled in pitch. It sends a current to the pitch torque motor, but the pitch torque motor is on the roll axis. Why is that? Remember what we said. If I put a force, it's felt 90 degrees ahead of rotation. So pitch torque motor puts a force on the roll axis, which is felt here, which is the pitch axis. So what do you have to remember? Okay, my sensor, so my electrolytic switch, my pitch electric switch will always be on the pitch axis. It will always send a signal to the pitch torque motor, but the torque motor will always be on the pitch torque motor will always be on the roll axis. So what we can say about the relationship between the torque motors and the axis of the aircraft or the axis of the gyro is if it's a pitch error, the torque motor, the pitch torque motor will be on the roll axis. If it's a error in roll, it will be sensed by the roll. Okay, roll electrolytic switch, which will go to the roll torque motor, which is on the pitch axis. So we now know why we've got an electrolytic leveling or erection system. It's to keep the gyro's axis vertical relative to the Earth's surface. We use electrolytic switches, and those electrolytic switches control a torque motor. So far, so good. Next thing you have to remember or understand that when the aircraft topples or when the gyro topples or moves in pitch, the electrolytic switch contacts will have the electrolytic fluid will complete the contacts, allow a current to flow to its torque motor. And the motor will always be in the opposite axis. And remember that. Pitch torque motor will be on the roll axis. The roll torque motor will be on the pitch axis. Okay. Are we all happy with the understanding of the leveling circuit and how we get the gyro back for getting its axis back to be vertical to the Earth's surface? Okay, are we all happy with that, or did anyone want to go through it again? I'm quite happy to go through it again, not a problem.
No problem, sir.
Right, so highlight it. Electrolytic switches. In straight and level flight, there'll be no supply to the torque motor. When the gyro topples or moves in pitch or roll, the electrolytic switch the electrolyte in the switch will complete the circuit, and the direction of current flowing through the motor will determine the direction of current at the torque motor, and that will determine the direction of the precession. Pitch torque motor on the roll axis, because the force is not felt until 90 degrees ahead of rotation. And the roll torque motor is always on the pitch axis, okay? Always on the pitch axis. Yep. Okay. Now, this has a problem, okay? These electrolytic switches are very, very good at what they do, okay? They're really, really good at what they do. But they can cause a problem, okay? And it's what's called turn errors, okay? Turn or acceleration errors. So let's look, I just want to go back to this here, okay? I want to go back to this here. And we're all happy. The gyro topples, gravity will cause the electrolyte to spread out and complete the circuit. What would happen if I went into a turn, okay? If I go into a turn, not only have I got gravity, I have a second force, and that second force is called centrifugal force. So now if I turn fast enough, okay, the centrifugal force could cause the electrolyte to spread out, completing the circuit. Okay, whoops. So causing one of the torque motors to start to precess the gyro. Even though the gyro is vertical, centrifugal force is making it think it's toppled. So this causes problems, okay? And it's something what's called gimballing error. We're not going to go into the depth of how that works. That's left for the B2s in advanced instruments. But what happens is during a turn, so the aircraft has banked, okay? The aircraft has banked. The centrifugal force causes, okay, so I'm doing roll, it causes now the pitch to move, okay? It causes the pitch to move. It causes the aircraft to go, the gyro, to precess the gyro nose down, okay? It causes the gyro to precess the gyro nose down. As soon as the aircraft comes back out of the roll, the gyro, rather than being straight and level, now has an error in pitch, okay? Now has an error in pitch because the roll, okay, here, the roll torque motor produces a force on the pitch axis, okay? Okay, but that force now, because it's what we call gimballing, it transfers the force from one here, so it's felt, it's produced here, but look, it applies a force here at 90 degrees ahead of rotation on the pitch motor, and it causes the pitch to drive the gyro down, okay? That's the basics of it. We're not going to go into more on that because it is quite complex, and this is basic instruments, not advanced instruments. But what you have to remember, gentlemen, okay, is when the aircraft, okay, when it says here, look what it says. I'm just going to highlight one little bit. That, oh, God, give me a strength. This bit here, when we start to turn, the aircraft starts to bank during a turn. Okay, it says there the centrifugal force caused the gyro, the electrolytic switch to move out, causing the gyro to precess inside the turn. Okay, as this precession increases, okay, the bank increases. Next bit, it says there the torque motors on the gimbal counteract to act this. Because basically it thinks it's toppled and roll. It's moved and roll. So it's trying to bring the gyro back up. But that force bringing it back up acts on the pitch torque motor. And what will happen is it also drives the nose down. Okay. And what happens is when the aircraft levels out, the error caused when the aircraft turned in roll becomes an error in pitch. So that's the first thing. All you need to remember, gentlemen, what happens with a gyro, an electrolytic leveling system, when the aircraft starts to turn, okay? It will during the turn, when the aircraft levels out, the error in roll will be changed into an error in pitch. Okay, just remember that phrase there. So during a turn, an error in roll becomes an error in pitch. It's not properly corrected. We're going to look at how we properly correct it. But you need to remember that little phrase there. So for gyros or a vertical gyro, when the aircraft banks and roll, it will precess it to become an error in pitch when the aircraft levels out. Okay, that's that little diagram in your notes. Okay, just remember that. Okay, just remember that part. Okay, it's not. We're not going to advance. We're going to the advanced people. The B2 is going to a lot more. That's as far as we're going to go into it, okay? Right, so how do we stop this from happening? Okay. What we can't do, we can't stop the centrifugal forces. Okay, we can't stop the centrifugal force. But what we can do is remove the electrical supply to the torque motor. Okay. And this is what we call erection cutout, roll erection cutout. The same happens in pitch, but we're just going to concentrate and roll. Okay, so what I'm going to do, if I'm going to have an error in roll caused by the roll torque motor precessing, causing a fault, that error to transfer onto pitch, if I cut out the supply to the roll torque motor, I'm not going to have an error. And as we all know now, if I remove any leveling circuit, a basic gyro, okay, has rigidity and always wants to stay in the same direction in space. So over a short term, the gyro shouldn't move. So basically during a turn, there'll be very, very little error for a rigid gyro. So what we're going to do is remove the supply, okay? So it's called erection cutout. And it says there, refers to the stopping of the precession of the gyro during long bank turns. Okay. The aircraft, again, uses tilt switches. Right. What we're going to happen here? So here's my tilt switch. Yep. Tilt switch. Anything, so straight and level flight, it's not going to do anything, okay? So now, look what happens. If I get an acceleration force, look, it would start to precess the gyro. Okay. So it says here, during a turn 5 to 10 degrees, the electrolytic switch will move and will cause the gyro to operate. Okay? But that's small. Now, if I get large centrifugal forces or the aircraft has a steep bank, look what happens. The electrolyte goes to one end. And as you can see now, there's my 28-volt supply. It can't complete the circuit. If it can't complete the circuit, the roll torque motor won't precess. Okay? It won't precess. So I've actually moved the supply to the roll torque motor. And that's what we call roll erection cutout. I cut out the supply, the electrical supply to the roll erection system. Oh, okay. Now, in your notes, I want you to remember a couple of figures, okay? In your notes. It says in your notes that roll erection cutout will happen when greater than 10 degrees of bank. Okay, so roll erection cutout happens when the aircraft goes into a steep bank greater than 10 degrees, or when the centrifugal force is greater than 0.18 gravity. Okay, so basically when the centrifugal force exceeds the normal gravity by 0.18. Okay, remember those figures. So you could be asked, what is roll erection cutout? Basically, it removes the supply from the electrolytic switch, the electrical supply from the electrical switch when the aircraft bank's greater than 10 degrees, or the centrifugal force is greater than 0.18 gravity. Okay, 0.18 gravity. What would happen if we didn't have roll erection cutout in my vertical gyro? So during a bank turn, there would be an error in roll, and when the aircraft leveled out, that error in roll would transfer to an error in pitch. Okay, that error in roll would transfer to an error in pitch. Okay, are we all happy about what roll erection is and the problems it can cause and how we get rid of the problem of the error in roll becoming an error in pitch? Are we all happy with that? Anyone got any questions on that? Anyone?
Len,
Yes.
this,
Hello?
can you summarize this from the initial, like very shortly? Like first of all, this error caused during the turn, we use the switches, right? Two switches.
Yeah.
To connect that turn.
I can't hear. You're breaking up a little bit. I can't hear what you're saying.
Sorry?
You were breaking up there. Can you say what you were saying?
I can
say
see.
Again.
Oh, I mean to say that I just want this summarized like very shortly. From like very first we got the turn error, right? to correct this tone error, we use 2 switches, mercury switches.
we just do right. Okay, I'll do a quick highlight here.
Yeah.
So you're happy about why we have the erection system to keep the axis of the gyro vertical. Agree with that?
Yeah.
So gravity will move the electrolyte to complete the circuit. So that's the erection system. Now, if the aircraft was to go into a bank turn, okay, so the aircraft starts to go. The aircraft is going to go into a bank turn. So the centrifugal force as the aircraft is yawing round, let's say, was going to cause the electrolyte, okay, to complete this part here. So we get a supply down through here. To the roll torque motor. And what will happen is it will try to counteract the roll. But remember we said the forces can act. So as during this turn, we have what's called gimballing. It's called a gimballing error. This force here also transfers to here, okay? And that causes a force on the pitch axis. So what happens now is that error in roll is the air. So, but what happens is at the same time, that error is also causing the pitch, the aircraft, the gyro to move in pitch. So now when the aircraft levels out, what we had was an error in roll, that's gone. We now have an error in pitch. So basically, we went to a roll, okay? And as soon as we come out, basically the artificial horizon is saying we're nose down or nose up. And if the pilot's in cloud, that's a problem. So we need to get rid of that problem of the gyro when we're in pitch. Sorry, when we do a bank roll, transferring its error into pitch when the aircraft levels out. Okay, and this is where the roll erection system comes in. This is where the roll erection system comes in. And it says there, during a turn, the error in roll, if not properly, okay, the error in roll becomes an error in pitch when the aircraft levels out. If not properly correct. Say again?
This is during normal turn as well, this error occurs?
Yes, yeah.
Okay.
Anything greater than 10 degrees of bank or 0.18 gravity centrifugal force. So it doesn't take a lot of centrifugal force to cause this fault.
Yeah.
So we need to stop the gyro, when the aircraft levels out, giving the pilot a wrong pitch indication. So what we do is we have this what's called roll erection cutout. And if you look here, this is what would happen on a small bank or a small centrifugal force. It would start to precess the gyro, but it would do it slowly. And the error wouldn't be that much. Now, so in between 5 and 10%, okay, the electrolytic switch will operate and trying to precess it. It will create a small error. Now, if the aircraft banks greater than 10 degrees, so the gravity will pull the electrolyte to one end, or the centrifugal force is greater than 0.18 gravity, all the electrolyte goes to one end of this little glass tube. And if you can see here, there is no supply. If there's no supply can get through to the torque motor, it can't precess and roll. And if it can't precess and roll, we won't have an error in pitch when the aircraft levels out. So what roller erection cutout does, it removes the supply to the taut motor when the angular bank is greater than 10 degrees or the centrifugal force is greater than 0.18 of gravity. Are you happy with that?
Yes, Link. Yes, got
Okay,
it.
good. Okay. Right. One last thing. We'll look at this here. Now, remember I said an attitude indicator or something called an attitude direction indicator. What an attitude direction indicator is like a remote, what we call a remote gauge. Okay. It looks like an attitude indicator, but the gyro controlling it will be like in the electronics compartment of the aircraft. So it's no longer one component with a face and a gyro in it. The gyro, like quite a lot of aircraft, will be remote in the, like say, the avionics compartment. So we'll basically be sending a three-phase signal, and this is operating like a little servo motor. Okay. So remote gyro, so it's going to get its information from the remote gyro or the inertial reference system, depending on the type of aircraft. Sorry about that. Right. We'll go for a 10-minute break, gentlemen. Okay, and we'll come back to do this. Okay, we'll have a 10-minute break, and we'll come back and we'll do the next part. Okay?
Okay, okay.
Thank you. understanding of a rate gyro? Yep. Anyone want to go through it again? Good. So, let's have a look at this and see it a bit better here. Okay. So, there's me looking straight down on the gyro. And now the aircraft starts to turn to the right. Okay. Starts to turn to the right. So therefore, that centrifugal force is felt at the front of the gyro. The precessional force will then act 90 degrees ahead of the direction of rotation. So imagine that it's rotating that direction. It's going to be felt at the bottom of the rate gyro, and it will cause it to tilt to the right. And you can see there, it starts to tilt to the right. Now, if you look at the spring force, okay, so that's my restraining force, okay? That down there is my precessional force. And if I put my pointer on, that pointer will come to the rest when the restraining force is equal to the precessional force, okay? And that will give me or indicate to the pilot his rate of turn, okay? Yeah, principle of gyro. So now look at this. That's going to happen. This is what it looks like inside my instrument. There's the gimbal, but it's attached to a pivot. So it's inside an instrument. There's the one, it's a freedom. There's my restraining force. There's my pointer. And these are what we call the indication marks. Okay, but these marks will tell me the rate of turn left or right. We can have up to 4 of these marks. Okay, we can have up to 4 of these marks. So what we're looking at is so, in straight and level light, the pointer would be like that. So basically, the pointer is in the middle. Okay, pointer's in the middle. Aircraft starts to turn. We now know the gyro precess, and we'll keep moving until the restraint is equal. Now these marks, okay, are called rates of turn, okay, rates of turn marks. This one here, the first one, we'll call that 1. Next one we'll call 2. This one we'll call 3. And this one we'll call 4. Okay. So an aircraft can have up to a maximum of 4 rates of turn, or 4 indicated rates of turn. Okay. And it would also be the exact same on the right hand side for the aircraft turning to the right. So what is this tell the pilot? So the pointer comes to red, he's got round half, is the pilot that he's doing 360 degrees in 1 minute. If the pointer was on the third scale, it would be 540 degrees in 1 minute, 1.5. Rate 4 is 720 degrees per minute. Okay. This is what the pilot will use. Now, we'll look at what the pilot would do. So let's say I had a rate 1 turn, okay? A rate 1 turn. So basically, I'm going to fly the aircraft until the pointer on my turn and slip indicator indicates 1. If I want to turn 90 degrees to the left, okay, remember what I said, in a turn, my compass could be inaccurate. And this is where the clock and the turn and slip indicator would come in. These are still fitted to all private aircraft, like all the little Cessnas, the Pipers, they're all fitted to that. Some helicopters and a lot of older aircraft, some of your 737 classics, your old 747s will probably still got this gauge. But a newer glass-cocked aircraft, you won't see this information. We'll talk about that in a second. So if I want to go from turn 90 degrees to the left, what I could do is move my aircraft to rate 1, start my stop. If rate 1 turn is 180 degrees per minute, how many seconds would I have to do turn at rate 1 to turn 90 degrees?
30 seconds.
30 seconds. That's it. And that's what the pilots do. If they wanted to turn 45 degrees at rate 1, it would be 15 seconds. Yeah. If it was 90 degrees at rate 2, how many seconds would it be?
15.
15 seconds, yeah. And that's all the pilot does. Okay. So just be aware, gentlemen, you could, so you have to understand what a rate 1, 2, 3, and 4, 1, 8, 2, 360, rate 3, 540 in 1 minute, and a rate 4 is 720 degrees in 1 minute. So you'd be asked the figures, but what you could be asked, is what I've just said, at a 1 turn, okay, the pilot wants to move 30 degrees, okay? It's going to be, so 30 degrees, well, that's 1/6 of 180. So it must be 6 of 1 minute. 1/6 of 1 minute is 10 seconds. Yep. So all you've got to do is work out. You might be asked something like that. Okay, but please remember what each turn represents. Okay. Now, some indicators, turn and slip indicators, have this wording, a 2-minute turn. Okay, so it takes 2 minutes to go 360 degrees. In 2 minutes. So 1 is 180 degrees in 1 minute. So 2 minutes, it does 360 degrees. So any indicator you can see here, this we found in like a small aircraft, like a small private aircraft, like a little Cessna, little Piper, something like that. And you can see there, it's only got 1 mark left and right. So the maximum this aircraft can have is rate 1. Rate 1 is 180 degrees per minute. Therefore, it must take 2 minutes to complete 360 degrees. So if you ever see, if you're asked if a turn and slip indicator is indicated as a 2-minute turn gauge, it must be rate 1. Rate 1 equals 180 degrees per 1 minute. So therefore it must be 2 minutes to complete 360 degrees, to complete a turn. So let's look at the turn and slip indicator itself. So we're now happy. That's the pointer. That's a tap. It will move left and right depending on the rate of turn. We were asked that earlier on. Somebody asked about the off flag. There's a little red off flag. So if we lose power, if the pilot thinks he's in straight and level flight and the power was off and he turned, this wouldn't move. So when the power's removed, there's a little off flag, little red flag. So when the power's off, this little flag drop gets pulled down by spring, pulled down. And when it's electrically powered off, a little electrical solenoid lifts it up. So that's the first part. The first part of a turn and slip indicator is the turn, the rate of turn. The next part is and it tells the pilot if he's doing what's called a coordinated turn. Okay, a coordinated turn. And a coordinated turn is when the aircraft banks, so it uses the ailerons to bank the aircraft. And at the same time, it uses the rudder to move the nose. So we can see here, if I bank the aircraft, gravity, okay, gravity can pull that ball down. So if I now turn to the right, so the aircraft is turning to the right, gravity, because the aircraft's banking to the right, gravity will pull the bead, okay, because this little glass tube has got a plastic bead, plastic little ball, and a glass tube that's got some sort of silicon fluid, clear fluid. So as the aircraft banks, gravity pulls it inwards. Gravity pulls it inwards. But if I'm banking to the left, centrifugal force is pulling it to the outside of the turn. And what we got was a coordinated turn, okay? And a coordinated turn, the two forces, gravity and centrifugal force, will be equal. So it says there, coordinated turn is when gravity is equal but opposite to centrifugal force. So if I've got the same force pulling the ball to the right, and I have the same force but centrifugal force pulling it to the left, the two forces are equal. And that's what's called a coordinated turn. And if the forces are equal, the ball is in the middle. So it tells us here it's called a coordinated turn, where gravity and centrifugal force are equal. From aerodynamics, you know, I bank the aircraft too steeply, the wing in the inside, I'm going to lose lift on it. You're going to fall out the sky. Centrifugal force is like a skid. Okay, I'm skidding. Therefore, we all know again the wing in the inside of a skid doesn't have the same amount of lift, and that will drop and the aircraft will fall out the sky. So I need to make sure that gravity and centrifugal force are equal but opposite, or the pilot needs to make sure gravity and centrifugal force are equal but opposite. So the ball will always be in the centre. It says there, part of a tube. This will be kept in the central position by gravity when the aircraft is straight level. Yep. In balanced terms, use the word coordinated turn. Okay. The ball is kept in the position by the resultant of gravity and centrifugal force. They're equal but opposite to each other. Okay. So, as it says here, straight level flight, gravity, straight down. The ball will be in the bottom of the curve. Now, in a coordinated turn, as you can see here, centrifugal force is trying to pull it to the inside of the turn. If the turn is coordinated, the results of the ball, beg your pardon, we'll keep the ball between the two lines. Okay. So we're going to look at what the indicators will read. You could actually decipher or tell the examiner what the turn and slip indicator is telling the pilot. Okay. So let's have a quick look. If the ball is to the outside of the turn, that means centrifugal force. Okay, centrifugal force is big ball is force. So what you say here, let's look at the ball is to the aircraft is banking to the right. Okay, the aircraft is banking to the right, and it's a steep bank. Gravity is taking it over. So if the aircraft is overbanked, if the aircraft will be the inside. If we don't have enough bank, okay, or the aircraft is skidding round, centrifugal force will take to the of this. We're slipping, therefore the ball will be to the outside of the turn. If it's overbanked, gravity will take over, pull it the inside of the turn. Okay.
switch.
On this, this is a diagram I used to explain it. All you've got to remember is when there's no power, okay? Okay, there's two positions of the switch. When it's powered, the off flag. Hold on. Here's the gauge, right?
Okay.
So no power. Okay, the off flag.
Off flag.
Like that. Yep. Okay, so you can see it.
Okay.
Right. Let me go clear that. Right. So off. So there's no power. That's what it'll look like. Now, okay, I'm going to put power on. And what happens is the electromagnet, basically the coil, the solenoid coil pulls the off flag. Okay, pulls the off flag up. So it's no longer seen in the front of the instrument. Okay. Does that answer your question?
Yeah.
So in a sense, there's not a normal position for it. There's the correct position depending on if there's power or there's no power to the instrument. Okay, Prakash.
It means basically centrifugal switch control the RPM of the DC power gyro. Yeah.
That's a diff. On this particular gauge, there's two. What it's just a separate centrifugal switch. This centrifugal switch is only controlling this. Okay, just when you're talking about this is centrifugal switch controlling the rotor, this one's controlling this one. There's two different centrifugal switches in this gauge. Okay, but just be aware of how the off flag works. Current flows through the coil, produces electric field, and will pull the off flag out of view. If the power fails, the electromagnet loses magnetism and a spring will pull the off flag back into view. Okay, so we lose the power, the off flag comes back into view. Okay?
Okay.
Right. And it says there, when the coil is energized from a supply of the correct polarity, the magnetic field in the iron core, and causes it to pull. Unfortunately, I haven't got time to show you these. Okay. Right. That's the basic gyros parts covered. Now we're now going to look at compass systems. Okay. We're going to look at compass systems. Okay. Look at compass systems. And the first bit we're going to look at is the Earth itself. Okay. The Earth is a big magnet. Okay. And without the Earth's magnetic field, we'd all be dead. All the solar radiation, the solar wind, and all the particles from outer space would actually burn us all up. So we need the Earth's magnetism. As you can see here, the Earth, it has its magnetic field, okay? But what we need to remember, gentlemen, is there is actually two norths, okay? There's the North Pole right at the top, geographically at the Earth, okay? Right at the very top. And then we have something called magnetic north, okay? Magnetic north. And magnetic north at the moment is about there. There's the geographic north. So you can see there's an angle between them, okay? All our compasses we use point to north, okay? But our compasses point to what's called magnetic north. Yep, magnetic north. Now, if you look at this magnetic field, it's no different to what you've got in a magnet, okay? At the ends of the magnet, the magnetic field comes in quite steep. At the side of the magnet, it runs quite straight, okay? And we need to use these magnetic fields because this is what my compass is going to line up against. My compass needle is going to line up with the lines of Earth's magnetic field. Okay, the lines of Earth's magnetic field are going to cause the compass needle to line up with magnetic north. So magnetic north, and this bit up here, the geographic North Pole, is what we call true north. Okay, and that's what we use our maps. So all our maps, all the grid squares on our map use true north as their datum. Our compass uses magnetic north as its datum. And you can see both magnetic north and true north are not at the same place. So that's going to cause us problems when we do navigation, when we use our compass. And we'll look at how we compensate for that later on. Okay, so remember, our compass needle lines up with the lines of magnetic north, but our maps line up with true north, which is right, what we call the geographic North Pole, which is right at the top of the Earth. Now, if that's not bad enough, look, I don't even see here. If you actually look here, I'll get me. If you look here, there's magnetic north. Yeah, look what happens. It's moving. You can see there's the time as we're coming through history. Magnetic north is constantly moving. Yeah, constantly moving. And what the geologists, the scientists say, that approximately every 170,000 years, the magnetic north changes. So the north becomes the south and the south becomes the north. And the reason why we know that is we can look at the rocks. And one of the prime places is the Himalayas. If you use your compass, a compass, and you go up close to the rocks in the Himalayas, the compass needle, every so many 100 meters, the compass needle changes direction. And that's because when the rocks were laid down millions of years ago, they aligned with the magnetic north at that time. So as you go up layers, the compass needle change, and that's how the scientists know. So the problem is now, not only is our magnetic north not in the same position as our true north, magnetic north is constantly changing. Again, that's going to cause us problems with navigating as well. I haven't really got time to go through that, but you can see, I'll just point out here, in what year was that? 2001, magnetic north was 81 degrees, 80 minutes north, and 110 degrees, 48 west. In 2012, it was 85 degrees north and 147 degrees west. So in the space of 11 years, it moved 4 degrees north and 37 degrees west. So it's constantly moving. So now my needle, okay, not only is not pointing to geographic or true north, it's pointing to magnetic north, but magnetic north is constantly changing. That creates problems when we navigate. Okay, so we're going to have to look at how we get around that. Okay, so we need to look at something called variation. Okay, we need to look at something called variation. Okay, I'll just hold on. Right, so I'm just going to put magnetic north here, just to help me on this diagram. So that's magnetic north, and that's true north. And if I draw a line, okay, this is about the equator here. Okay, if I draw a line from the equator to magnetic north, and I draw a line from this point on the equator to true north, you can see there is an angle, okay? And that angle there, okay, that angle there is called variation, okay? And variation is the angle between true north and magnetic north, okay? Please remember that. You could be asked, define variation. Well, variation is the angle between true north and magnetic north. Or what is the angle called between true north and magnetic north? It's called variation, okay? We're going to look at that, and it also changes, the angle of variation also changes where you are on the Earth. So it gets even more complicated, okay? So here's this chart, okay? If we look at this chart here, this is the angle, this is the variation. So 0, minus 10, 20, 30. That is the angle between true north and magnetic north. And you can see here, it also changes over time. Okay? Changes over time. And if you look here, it's minus 20 there, plus 20 there. So one angle, one will be to the right of true north and one will be to the left of true north. So this angle of variation can have a polarity, positive or negative, okay? Right. As a definition for you here, gentlemen, for you to learn, okay? As a definition here for you to learn. And if we look here, okay? If you look at the green line, that's 0, okay? 0 means at this point here, the your magnetic compass needle would point directly to true north. So there is no variation at that area here. We look at this blue line, okay? It is 10 degrees. So it's going to be 10 degrees. The variation is going to be 10 degrees, let's say, to the left. We look at this one here, it's plus 10 degrees. So the lines, the variations between magnetic north and true north is plus 10. So with all these different angles. Now, the other thing you can look at, that actually is the magnetic south pole. Magnetic north is here. So what we can say as well, the poles are not at the geographic north and south, okay? But these lines of variation, okay, we give them a name, okay? So if I look here, all these points, it's joined with that minus 10, okay? It's called a isogonic line, okay? So any lines of equal variation are called isogonic lines. Please remember that. Okay. The green line, okay, where there's zero variation, that's called agonic. It's an agonic line. So a line of zero variation is called an agonic line. Other lines of equal variation are called isogonic lines. Okay, isogonic lines. Remember that definition. Okay, are we all happy about that? So you need to be able to define variation. That's the angle between true north and magnetic north. The lines of variation, if they're zero, they're called agonic lines. And if they are lines of equal but not zero variation, they're called isogonic lines. Okay. So you can see there's your variation. Okay, they're giving you, as you can see in that line there, there's the magnetic north. Okay, and that's the geographic north. And depending where you are in the world, that'll be that angle of variation. Okay, and you can see even across the United States, look, it's 11 degrees west in New York, and it's 17 degrees east in San Francisco, the other side of the continent. So you need to be able to define what variation is, the angle between true north and magnetic north. You need to be able to define an agonic line. An agonic line is a line of zero magnetic variation, and an isogonic line is a point of equal magnetic variation. So what does this do for us? Okay, what does this do for us? Well, it causes us problems. Okay, I'm going to come back to that slide. I've got a better slide to show you in a minute. Now, here's an old-fashioned compass. Some of you go walking in the hills, you'll use it. And if you can see here, look at it. There we go, old-fashioned compass. You can see the headings, and you can see the needle. Okay, we usually have a red and a blue needle. In fact, I've got one here. Now, I don't know if you're able to see this in the camera. I'm going to try and turn it. Can you see it? You see the compass? See it? You got a blue needle. Try. Hold on. I can't. I'm trying to show it too well. Hold on. If I take the back, if I take the background, it might show. Hold on. So let's have a look, see if it'll show it now. That's a bit better. Okay, you can see it now. You've got a blue end and a red end. The red end is one always pointing north. Okay. Yeah. So that's always going to point to north. Okay. Now, if you actually look at the needle in what we call now a direct reading compass, okay? If I now just draw a little diagram here. So we've got a pivot point. Okay. And then we've got the needle resting on the top. Okay, resting on the top. And as I said earlier, that my compass needle Let's try again. My compass needle wants to line up with the lines of the Earth's magnetic field, the north to the south, north to the north, and the south to the south. So that's one force, okay? But what I'm going to say to you now, gentlemen, that the Earth's magnetic field comes in two parts, okay? The first part is what we call the horizontal. And the other part is the vertical. And what the two parts of the Earth's magnetic field does is the horizontal part, that's what my compass needle wants to line up with. That gives it the direction. The vertical part is trying to pull it down. Okay, and what's going to happen is, it's just like any pivot, gentlemen, it'll get to the point where you can't get any movement. It just sticks, okay? Because it's what's called a dual cup mount. And basically, it'll stick, it won't move. So, my direct reading compass only really likes to work with the horizontal part of the Earth's magnetic field. Okay, so let's have a look at the Earth's magnetic field. Here's my magnetic north. Here is the equator. Now let's look at the lines of Earth's magnetic field. At magnetic north, you can see they're almost vertical. Yeah. So basically, I've got maximum vertical. If I look now at the equator, I can see that the lines of magnetic field are parallel, okay? So I can see here, I have maximum I've got the maximum horizontal part. Now, gentlemen, I said that my compass needle likes to line up with the horizontal part of the Earth's magnetic field, not the vertical part. So, if that's the case, that my compass needle, okay, you can see here, will line up best or most efficient at the equator. Why? Because I've got maximum horizontal force and minimum vertical. Yeah. I come to magnetic north, I've got maximum horizontal, minimum horizontal. So my compass needle, okay, is most efficient at the equator, and it's least efficient. If it's most efficient at the equator, where is it least efficient? Either magnetic north or magnetic south, i.e. the poles. Okay, the magnetic north pole or the magnetic south pole. Now, we need to know that. So you need to know in a direct reading compass, where is your compass most efficient? It's most efficient at the equator. Why is it most efficient at the equator? Because my compass needle wants and likes to line up with the horizontal component of the Earth's magnetic field. Okay? Horizontal component of the Earth's magnetic field. And as I now start to go from the equator to the poles, the horizontal component you can see now is starting to curve. Okay? That line is starting to curve. So therefore, the horizontal component is decreasing, and the vertical part is starting to increase. And the further north or the further south you go, the vertical component increases, and it will get to the point, okay, and it's approximately 82 degrees north and 82 degrees south, that your compass, your direct reading compass, doesn't work. Okay. Now, one of the things, I used to work up in Norway. Okay, Norway. And the big airport where we used to go was 82 degrees north. It's a city called Tromsø. Okay, it's a largest city, let's put it that way. It's 82 degrees north. Okay. This is one of the reasons why, if I wanted to fly to Scotland to Nepal, the quickest way is actually over the poles. We can't, commercial flights still don't go over the poles because our compass systems are still not accurate. Okay, we can't guarantee our compass or our GPS or our radio signals will work over the poles. That's why we don't fly over the poles at the moment. So we're happy about that. So you need to understand, where is my direct reading compass most efficient? It is at the poles. Why? Because it's lining up with the maximum component of the Earth's magnetic field. So where is it most inefficient? It will be at the poles. Right. So this angle, okay. Let me get my, there we go. So let's look at this here. So that's the horizontal component. And that's the vertical component. That angle of vertical will change the further north I go, or south. And you can see now we have an angle, okay? And that angle is called the angle of dip, okay? So you may have to be defined what the angle of dip is, or what dip is. And dip is the angle between the horizontal component of the Earth's magnetic field and the vertical component of the Earth's magnetic field. Okay, you have to understand and define dip. It's the angle between the vertical part of the Earth's magnetic field and the horizontal part of the Earth's magnetic field. We're going to come back to that little diagram in a second. So that's that dip, okay? One thing as well, is we give those lines. And what you can say about the angle of dip, it increases as the further north or south you go. It is roughly within a few degrees the same as the latitude you are at, okay? My latitude in Scotland is 53 degrees north, and my angle of dip for my compass is approximately 55 to 56 degrees. So you can see it's very, very similar to latitude. So lines of equal dip, okay? Lines of equal dip, so equal values of dip is this here, okay? And we call it, so these lines here, okay? So anywhere on that line has an equal value of dip, that angle of dip. And that line is called an isoclinal, okay? An isoclinal. So a line connecting 2 points of equal magnetic dip are called a isoclinal, okay? You could be required to define what an isoclinal is a line of equal magnetic dip. Or you might be asked, what is a line of equal magnetic dip called? It's an isoclinal, okay? An isoclinal. Now, I said the further the north you go, the more inefficient my compass becomes until I get to approximately, it's about there. Oh, come on. Okay, 82 degrees north. 82 degrees north, my direct reading compass really doesn't work. It's basically like me going like that, okay? Near the vertical, the needle doesn't move, okay? The needle, you can see there, doesn't move because the pivot point, the friction at the pivot point is very, very big. It doesn't move. But, okay, but I can do something to help my compass be more efficient, okay? To help my compass be more efficient. Okay. Now you've all probably seen one of these. Yeah. Standby compass in your aircraft. Yeah, you've all seen one. You've all got one. You ever seen one, have you?
Yeah.
Yes,
Yep.
we have seen.
So
Yeah.
depending on your aircraft, it might be sitting in the window, or I think in the A320, it's like your little press and it'll pop down. Is that correct?
Yes. Yes.
Yeah. So you've got every aircraft by regulation must have one of these. What we do with this compass rather than a basic compass, because this compass is still affected by dip. Okay, this compass is still affected by dip. But what we're going to do is we're going to mount it, we're going to pivot it slightly different from my basic handheld compass. Okay, we're going to pivot it different. When I can get the next page over. Right, so let's have a look at my normal compass. Right, there's the pivot. there's the needle, okay? And the further north I go, I'll have a small amount of horizontal and a large vertical. And at 82 degrees north or south, it stops working. But we can do something, gentlemen, to help the compass. I can make this compass go 3 degrees north, more north, before it stops working than this. So I actually can get my standby compass, again, which is still a direct reading compass. I can make this one go up to 85 degrees north. How do I do it? Now, we'll look at that picture. It doesn't, I'll explain it, and then I'll draw you another little diagram to explain it. What we're actually going to do is, we'll put the center of gravity of my compass needle, or we're going to call it the compass bowl, below the pivot point, okay? So what we're actually going to do is, here, I've got a large amount of dip on that side, no vertical on that. But what I can do, if I have the pivot point below, I've got a force called and gravity acts on both sides. So what it's doing is pulling down a little bit more on this side. So it pulls it down, there's less friction on the pivot, and that is how we can increase the latitude we can use our direct reading compass. So I'll draw you a better diagram. So what we've got now is basically in here you've got what's called a compass bowl. And if I take a side, cut it in half, it looks like this. So basically that would be written like north 330, etc. Okay, and that would be like south 180, 160, etc. Right. So what we do now, there's the pivot point. Yep. So now it's hanging down. So what I can say is the center of gravity is there and there. So my center of gravity is now below the pivot point. And if I put the center of gravity below the pivot point, gravity is going to act equally on both sides. So what it's going to do is it's going to pull what we call the compass rose or the compass bowl down, allowing it to go north by another 3 degrees up to 85 degrees north. So how do I reduce the effects of dip on a direct reading compass? I put the compass bowl or the compass rose below the center of gravity of the pivot point, okay? I put the C of G below the pivot point, so please highlight that, okay? So how do I reduce the effect of dip on a direct reading compass? I put the center of gravity below the pivot point. I put the center of gravity below the pivot point. Any questions on basic magnetism? Okay, so the things we've got to remember is the definition of variation. That's the angle between true north and magnetic north. Lines of equal variation are isogonic lines. Lines of zero magnetic variation are agonic lines. My compass needle wants to line up with the horizontal part of the Earth's magnetic field. Therefore, a compass is most efficient at the equator and least efficient at the north and south poles. Why is the compass most efficient at the equator? It's because it's got the maximum amount of Earth's, the horizontal part of the Earth's magnetic field. What is the angle between the horizontal part of the Earth's magnetic field and the vertical part of the Earth's magnetic field? It's called
Angle of dip.
correct, angle of dip. I'm glad you remember that because for some reason I clean forgot it in my head. Don't know why. Must be Friday. It's been a long week. Okay. So how do we reduce it? And how do we reduce the effects of an angle of dip on a direct reading compass? I move the center of gravity below the pivot point. Okay. I move the center of gravity below the pivot point. Okay. So any questions on the basics of terrestrial magnetism? No. Okay, gents, we'll go for a quick 10-minute break. I need to go to the toilet. I'm getting old. It happens when you get old. Okay.
Ian,
So yes.
Hello, Ian.
Yes.
What was the line? Center of gravity below pivot point for what?
If I put the center of gravity below the pivot point, I reduce the effects. Like here, I reduce the effects of dip on my direct reading compass.
Okay.
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 So we'll go for a 10-minute break. We'll come back and then hopefully we'll get finished for today. Hurrah! Okay, I'll be back in 10. Just need to go to the toilet. Oh. How are we doing, gentlemen?
Lynn,
Yes.
I have one question.
Yes, please.
Like, why we don't need the erection system in the turn coordinator or turn and slip indicator?
Okay, I'll explain. I'll go back and do it again. Right, can you wait till I finish what I'm doing and we'll go back to do it right at the end?
Sure.
Okay.
Okay.
In fact, no, we've got a couple of minutes. I'll do it now.
Sorry?
I'll do it now. Okay. Right, so let's have a look at this here. We'll get rid of the. Now, in a turn and slip indicator or a rate gyro, okay, because the rate gyro, we said we have, there's my pivot point, yep. So it's equally balanced either side. But here's the thing why we don't need an erection system. See the restraining force? It keeps it, see the spring? Could be a spring or a piston, but we call it a restraining force. That keeps it level. Okay, so mechanically, it's held to be level. To answer your question?
That means it's mechanically it's balanced by the mechanically
Yeah, basically. So basically, when it's not powered up, it's held in the correct position. When it's running and there's no forces on it, it's held in the correct position. Only time that the gyro is going to get forced away is when we get a precessional force. But when that precessional force is equaling up to the restraining force, again it comes to rest. Okay, so that restraining force keeps it level. Okay, all the rest of the time. Okay.
Erection system function is done by here restraining force, right?
Yeah, but basically that's only going to be the erection system is basically used on our vertical gyros, and to some extent we will look at the horizontal, the compass gyro later on. Okay. Yep. But on this one, it doesn't have an erection system because mechanically it's held by the restraining force in the correct position.
Thank you.
Okay. Right. Okay. So that's the Earth's magnetic field. Okay. So navigating, you can see we've got a few problems already by just the Earth's own magnetic fields and the problems it has. But let's talk about the aircraft. Okay, our aircraft are made of steels, some ferrous metals. Okay, some of you are going to say, well, we've got magnesium alloys for frames and we've got carbon fiber skins. Yes, you have. But some of the gearbox, some of the mechanical, some of the motors, they're all made of metal. Okay, and certain metals have what we call ferromagnetic properties. Therefore, they act like magnets. So this is what we're going to look at now. And one little thing we've got to go through before we look at individual things, magnetic material. Materials are classified into 3 groups, okay? The first one is Group A, hard iron, proper old-fashioned steel, steel and iron, okay? Group B is called semi-hard iron, okay? We'll look at that in a moment. That's probably the worst group of materials to have on the aircraft. And group C is soft iron. Okay, soft iron. I'm going to tell you copper is classified as soft iron. I'm now going to, we've now told you what they are, I'm going to define them. Okay, group A. It says group A are materials that are very hard to magnetize, but very hard to demagnetize. So basically, they're permanent magnets. Okay, they're a permanent magnet. Group B are moderately difficult to magnetize and moderately difficult to demagnetize. Okay, and one of the things is with that is, if it's magnetized, it can be demagnetized. I could have a bit of magnetic material, it's what we call group B or semi-hard. And one of the ways I can demagnetize it over time is shock and vibration. It can actually demagnetize it. And we'll look at what that can do to my aircraft. The other thing is, if it's moderately difficult to demagnetize, I can also, it's difficult, but I can also magnetize it. And one of the things is, if I have a lightning strike hits an aircraft, if it goes through a metal frame, it produces a high current. If it produces a high current, it can produce a magnetic field. And if it can produce a magnetic field, okay, it can actually do something what's called polarize the metal. Some of the metals become magnetized, but over time, that magnetism drops off. So you can see things that can, we'll look at what that can cause difficulty. And the next thing is soft iron. And I said copper. Ian, I hear you say iron is not copper and copper is not iron. And I would have to agree with you. But it's the classification. Soft iron is something that is very easily magnetized and something that's very easily demagnetized. And I said copper. And if you put a magnet between a copper pipe, the magnet won't stick to it. But if I put a current through a copper wire, that current produces a magnetic field. I switch off the current, that magnetic field disappears from the copper wire. So you could be asked to define what the three groups of ferromagnetism are. Group A, hard iron, very difficult to magnetize, very difficult to demagnetize. Group B is semi-hard iron, okay, which is moderately difficult to magnetize and moderately difficult to magnetize. And it's the worst one because it can change its value all the time. And C is soft iron, okay, soft iron, copper, you put an electric current through it, it'll magnetize, switch off the current, it demagnetizes. So why are we talking about these? Why are we talking about these? Remember, my compass needle wants to line up with magnetic north. So now if I get, I don't know if you can see this well, okay, I'm going to try and see it. I'm going to put, can you see the needle, gents?
Yes.
See what happens to the needle?
Move.
It moves.
Yeah.
Right. So I put a bit of metal, okay, a bit of ferrous metal beside my compass needle. It moved. So now my compass wants to point to magnetic north. But if I have a bit of magnetized metal, it'll pull my needle away from north. Now we can cope with hard iron. We'll look at something called a compass swing. We can get rid of we can compensate for it, because hard iron is there all the time. It doesn't change. Soft iron is when we got a current going through a copper wire. So when I want to check my compass system out and I try to make it accurate, I'll get my compass to read correctly with all the systems I require on the aircraft on. So now when I set my compass up, the hard iron won't change. All the systems on the aircraft, when it's powered up, are on because I'm going to be using them in flight. So once I've set my compass up with all the power on the aircraft, the soft iron doesn't matter. Semi-hard iron, things that change, if it starts to become stronger, no, semi-hard iron magnetism, or weaker, my compass needle is going to move. My navigation is going to become inaccurate. So we've got to be very careful of that, okay? And we talked about things that can cause there of actually materials that are very magnetic. And I did say steel. Yep, iron. Believe it or not, there's other metals that are even more magnetic than iron, okay? One of them is cobalt. Yeah, one of them is cobalt. Who's ever used a cobalt drill on an aircraft? Doing repairs, putting new rivets in, doing a modification? Or anyone seen some of the sheet metal guys using a cobalt drill? Cobalt drills go through steel, easy. Yep. Haven't seen someone use a cobalt drill? Anyone? No? Years ago, when I was the shift chief, the shift boss, we got an aircraft, it just came out of modification, deep maintenance. And it went for its first compass swing. We couldn't get the aircraft, we couldn't get the compass to read correctly. When we were in, doing a check the components, and I looked underneath the frame it was in, and there was about ½ centimetre of a drill bit underneath, well, we'll call it the compass at the moment, but what was detecting the Earth's magnetic field? It was about ½ centimetre of a cobalt drill bit. It completely threw off the compass system. So be very aware of that. So things that can be made magnetic are steel and iron, yep. Cobalt, tungsten, nickel are the three big main ones, okay? Steel, cobalt, nickel, and tungsten, that's it. So they're the main metals we can make magnetic. Right, we've got to look at these magnetic lines. It's caused by our materials in our aircraft. And it's the exact same we talked about a magnet in Mod 3. The lines are unbroken. Exact same with our Earth's magnetic fields. That's posh words. Next bit, it poses a definite direction of strain. Okay, if you want to put that in your notes, okay, beside it, what that means, it goes from north, oh come on, give me a break, to south. Yep, That's all it means there. They always go from north to south. They're elastic in nature. I can actually stretch them out. Okay. Here's the best thing. They like to go through ferrous metals. Magnetic fields don't like to go through the air. So they like to go through the metal. And if I put a magnetic field through a metal, we concentrate these lines of flux. And the last thing, but any magnet, like poles repel, unlike poles attract. But these two here possess a definite direction of strain. Okay, that's going to indicate what they're going to do to my compass needle. And this one here, they like to pass through ferrous metals. Okay, they like to pass through ferrous metals. So it's like this. So I've got a bar of iron. Okay. I've got the Earth's magnetic field. Right? But when it starts to come towards the iron, those magnetic fields concentrate in the iron. Okay. And if they concentrate in the iron, that iron becomes even more magnetic. So we have a problem. Okay, these two here, and depending which way the magnetic field was going through that bar, will determine whether it would be that would be north or south, or vice versa. So remember the facts about lines of magnetic fields. Now, one of the things we used to do years ago when I used to work in the electrical workshop repairing generators, motors, etc., is we used to get, in some aircraft, we used to get motors and generators and some heavy current machinery out the aircraft because they were they'd gone too magnetic. Now, what they used to do years ago, probably up to about 1970, they used to go round the aircraft, and I'm not joking, they got a compass and they would go to certain components and see how far it pulled the compass needle away. And if they become very magnetic, they could cause the compass needle to be incorrect, the compass to be incorrect. So they used to demagnetize them, okay? And the word for demagnetizing is this word here. It's called degaussing, okay? Degaussing. And what we use is an AC field, okay? An alternating field, an alternating current, which will produce an alternating magnetic field. So what is going to happen is, on the positive half cycle, I'm going to have a north, negative half cycle, I'm going to have a south. And what it's going to do is get rid of the inherent or the hard magnetism of the components, okay? And degaussing, okay? So you have to understand what degaussing is. It's removing or demagnetizing components in the aircraft. How it's done. We get an AC supply. We put it through a coil and we move that coil through the component. But we must always do it east-west. Okay, because if a component has become magnetized, there's something called domains, and what they've all done is they've actually lined up with magnetic north. Okay. So now, if I put the degausser east-west, okay, I move it across it, what it does, that changing, what happens is these domains all become random, making them component non-magnetic, making the component non-magnetic. Okay, so how do you demagnetize components on any, well, components? We use a degausser. How do we degauss? We use an AC supply and we pass it over the component in the east-west direction. Okay, please remember that. Okay, degaussing, we do it east-west. Okay, east-west. Now, are we all happy with that? Yep. So, as I've said already, aircraft and aircraft components are going to have various levels of strength of magnetic fields. As you all know, if I've got a nice generator, the case is going to be of some sort of steel. It's going to have some sort of magnetism in it. If I have a motor, it's going to have iron coils in it. It's going to have an iron case. So it's got some sort of magnetism. My copper wires, as soon as I put a current through, produce a magnetic field. So my whole aircraft is a whole load of different components, all with a magnetic field. So now when I come to my little compass, it doesn't stand a chance, does it? Okay, it doesn't stand a chance, but we're going to do things to the compass so we can actually make it read very, very accurate. So what we've got to look at is how the aircraft's own magnetic field, caused by its own all its components on the aircraft, affect the aircraft itself. Okay, it affects the aircraft itself. So can I say that even though my compass needle wants always to point to magnetic north, but because of the magnetism of the aircraft, my compass needle might point here. So there's my compass needle. Yep. So as I said, the aircraft does all its navigation with its compass relative to magnetic north. But if my compass needle isn't pointing to magnetic north, I'm going to get lost. Okay, I'm going to get lost, I'm going to run out of fuel, and I'm going to crash. So we need to do something about this. Okay. Right, so now we have this angle. Okay, we have the angle. There we go. So that's the magnetic north. Okay. Okay, and this is my compass needle. Okay, and now we've got, you can see there's an angular difference. And that angle there, okay, we call the angle of deviation. Okay, and deviation is the angle between the magnetic north and what the compass is actually reading. Okay, so if my compass needle magnetic north is 0, 0, 0, 0, and my compass needle is reading 340, that angle must be 20 degrees. Yep. So the deviation, okay, caused by the aircraft own magnetic structure, in this case, is 20 degrees. So the compass has deviated away from magnetic north by 20 degrees. Okay, it's deviated away from magnetic north by 20 degrees. Now, as it says here, this deviation, again, like variation, has a polarity. It can be either positive or negative. Okay, now I'm just going to show you a way to remember this. I'm going to draw a clock and a compass. I'm going to make it one face. Okay, so well, right. Imagine that looks like a nice round clock. 12 o'clock, 3 o'clock, 9 o'clock. Yep. So that's the clock. Now imagine it's my compass. North, east, west. Yep. If I go in this direction, okay, we call that clockwise, don't we? And we always think clockwise is a positive movement. This here, going that direction, is anti-clockwise. And if people are anti, if anything is anti, must be negative. So that's negative, and that's positive. Somewhere in your notes, gentlemen, or in a bit of paper, draw this, okay? I want you to draw it, because what we're going to do now, we're going to look at the relationship between compass and magnetic north. We're going to look at magnetic north and true north. Okay, we're going to look at the relationship between the two of them. Okay, so you can see here at 12 o'clock, that's north. Any movement clockwise must be a positive number. Again, north, any movement west is anti-clockwise, is negative. Okay. I'll give you a couple of minutes, just a minute or two, just to draw that down, gentlemen. Okay. It will help you for the next bit we're going to do. Have you all drawn that down, gents and ladies? Or gents?
Yes.
Okay, so what we're going to look at now. Remember I said we had, I'll just draw this up here. Magnetic north and true north. Okay, that angle was called variation. Agreed? And now we know we have, I didn't do that. So on top of that, we now know we've got a magnetic north and my compass heading, okay, or what my compass is reading. And we now know that angle is called deviation. And remember I said when we talked, I showed you the the picture of the variation. Some of it was positive, some of it was negative. So what I can say here is my variation, if it's east, it must be a positive value. If it's west, it must be a negative value. And go back to deviation. If the deviation causes the compass to go west, it'll have a negative value. And if it causes the compass needle to go to the deviation to go to the east, it must have a positive value. So if you can remember that clock and that compass, positive and negative, this will help you out for the next bit. Okay, are we all happy with the understanding of that, please? Yep.
Yeah.
Okay, good. I'm just trying to find my little arrow again. So now, as it says here, deviation, if it's east, is positive. That's what I've just said. If it's negative, it's anti-clockwise or west. Okay. Not going to worry too much about it, right? So variation is the angle between true north and magnetic north. I'm going to come back to this thing called, if you look here, I've got compass. So we're going to do a little bit of calculation, gentlemen. Compass, deviation, magnetic, variation, true. Okay. So compass heading, what the aircraft compass is actually heading, and magnetic north, that angle was deviation. The angle between magnetic north and true north was variation. Okay. If you're ever involved in a compass swing, we need to understand that. So we actually, I don't know if you got Cadbury's chocolate out in Nepal? Anyone?
Yes.
Right. Okay. So how we remember this? We have Cadbury's. Okay, you can look at it there. Cadbury's, there's a dairy, there's milk, and it's very tasty. So Cadbury's, dairy, milk, very tasty. Cadbury's, C. Dairy, D. Milk, M. Very, V. Tasty, T. We're going to look at how we can calculate any one of these. Okay. So let's look at this information here. Okay. There you go. Compass, Cadbury's, D, dairy, milk, magnetic, very, V, tasty, T, true. Okay. Very unlikely you're going to get this, but you can see here, 100 T, that's true. 104 C, that's what my compass is heading. 109 is my magnetic heading. Deviation and variation. We can look at this, okay? 104, okay, my aircraft is heading 104, but the aircraft has a deviation of +5, and we know plus is also east. So 104 plus 5 is 109. The angle between magnetic heading or magnetic north and true north is variation. So 109 minus 9 or west gives me 100. Yeah. That makes sense, doesn't it? It's basic adding.
1 second, sir.
Yep. So you can look here. So I'll just draw up here. So there's my compass. D, M, B, T. Cadbury's Dairy Milk, very tasty. So C stands for compass heading, and the compass heading was 104. The deviation is 5 east, and we know 5 east is clockwise, so it's a positive value. So 104 plus 5 gives me the magnetic heading of 109. Yeah, 109. 109, the magnetic heading, we have a variation of 9 west, okay, 9 west, and we know west is a negative number. So 109 minus 9 is 100. Okay, 104 plus 5 is 109. 109 minus 9 gives me 100. Okay.
So west, how it comes?
Pardon?
West. How it comes the west variation?
I can't hear what you're saying.
So west, how it comes the west minus 90? I didn't get that.
Okay, remember I told you to draw this. So you look here, there's north, there's west, yeah. And because it's anti-clockwise, we say anti-clockwise, we think about anti being a negative. Yep. So anything goes anti-clockwise, we don't think it is a negative number, it's negative. Clockwise, we always think of positive. Yep. On is a positive action, which is clockwise. Off, anti-clockwise, we always think about that as off is negative. So you can see there how we work out minus 9. You get that now?
Okay, I got it.
Got it, right. Now, oops, let's go back to the sheet. Okay, got another one to show you. 304, yeah, so it's got a aircraft, is compass is saying it's going to 304. There's a deviation from the aircraft's own magnetic structure of 4 west. And 4 west we know is a negative number. So 304 minus 4 gives me 300. Magnetic north, magnetic heading of 300, a variation of, it says there 10 east. We know 10 east is a positive number. 300 plus 10 gives me 310. Okay. Yes.
The sign convention for the variation and deviation is same.
Yes, the positive or negative, yes. So if it's west, it's always a negative number. If it's east, it's always a positive number. Okay.
Like in the for example, I have given the magnetic heading of 300, 200, and the true heading of 300. So I have asked to find out the variation.
Yeah, I'm going to look. I'm going to show you how we can find out an individual one in a minute. So I'm not ignoring your question. I'm just going to come to it. Okay.
Okay.
I'll show you what we're going to do in a second.
Okay.
Okay. Now, a couple of things we need to look at. Just go through this one now. It says, look, compass 61, deviation plus 14. 61 plus 14 is 75. 75 plus 15 gives me 90. So one thing we can say, gentlemen, if we're working from left to right, we can follow the sign. We do what the sign tells me. So 61 plus 14 gives me 75. But say, for instance, now, okay, I had to work from right to left. So what we're going to do, if we're going to go to right to left, what we'll do is we change the sign. So now, if I'm going this direction, okay, I'm going to go from right to left. So 90, the variation is plus 15, but because I'm going in the opposite direction, I'm going to make that a negative. So 90 minus 15 gives me 75. 75, because I'm going this direction, I now make that a negative. So it'll be 75 minus 14 gives me 61. So a couple of things to remember. When I'm working out left to right, I do what the sign tells me. If I go from right to left, I change the sign. Okay. Okay. Now, Yadev hopefully sent out some sheets this morning. Did you all get them?
Yeah.
Okay.
Yes, sir, we got.
Could you open them up, please? Okay, either if you got them printed or look at it on the screen and I'll go through a couple. Okay, I've given you a whole sheet and you'll actually find out there's the answers as well. Okay, so you can have a practice over the weekend. Okay, it's a little bit of work for you to do as well as reading. Okay, let's start with an easy one. Okay, I'll start with an easy one. Okay, I'll start with this one here. Okay, oh, in fact, let's get a different. Let's start with. So I'll start with. Yeah, I'll start with this one. So 214. Okay, so my compass is reading 214. Yeah, compass is reading 214. My magnetic heading is actually 215. So to go from there to there must be somebody's put the microphone on. Okay, so I've got there 214. I need to go to 215, so it must be +1. Yeah, 214 plus a deviation of +1 gives me 215. Okay, if I have a variation, I think that one is, hold on. I'll just get that one up. Hold on, here's my arrow. Yep, that one there is, where's my arrow? Where's my pointer? That there is 5. Oh, come on, give me a break. That's 5 west. Sorry, that should be changed. So it's +1. So 215, 5 west. 5 west is negative. 215, take away 5 gives me 210. Yep. Let's go to the one below. Okay, we do this one now.
Sir, excuse me, sir. That
Yes.
west, how it came again?
What do you mean?
That 5-degree west, how it came?
How did I do it?
Yes, I didn't good. I didn't understand, sir.
The
You
यो
didn't understand.
करेक्ट गरेको उसले वेस्ट छोडेको थियो त्यो करेक्ट गरेको this will be the exact question.
West becomes negative. So
Okay,
215 take away 5 gives me 210.
Okay, sir.
Yep.
Okay.
Let's look at this one. Okay, let's look at this one here. Now it was 359. Okay, 359. But I'm going this direction. Okay, 359. East is always positive. Yep. but I'm going in the opposite direction, so we're going to make that -1. So 359 -1 becomes 358. Okay, 358. Okay, I've got one west. One west is usually negative. Yeah, but because I'm going the opposite direction, I'm going to make that positive, and that'll become 358 plus 1 gives me 359. Okay, 359. Okay, what I would like you to do, gents, is have a go, okay, at, if you've got the sheets here, or just write it out. If you get asked any of these in the exam, the first thing you do, you write on your bit of paper, Cadbury's, dairy, milk, very tasty. I can still remember this from 1980, whenever I did my course. Okay, so I would like you to have a, yes?
Please explain the second one, this 359.
Okay.
Plus, if it is east, then it should be positive.
Yeah. Okay, I'll go through it again. Now, when I said we do or not how we normally do math or read, we always go from left to right. So we follow the sign. If I go from right to left, so I'm going this way, I'm going in the opposite direction. So the sign must change. Okay, I must change the sign. So we look here, we've got 359. I've got east, and we now know east is actually a positive number. But because I'm going this direction, we must make that a negative number. So 359 minus 1 gives me 358. Yep. So now I want to find out my aircraft, what my aircraft is reading, what my compass is saying. So 358. And my deviation, so the angle between my compass and magnetic north is 1 west. And we know 1 west is a negative number. But because I'm going from right to left, we make that, we change the sign so it goes from a negative to a positive. So 358 plus 1, that becomes 359. Okay, yeah. And if you look on the sheets here, 358, or 358, 359. Okay.
Yeah.
You have those sheets here. Okay. So what I'd like you to do is have a go at the third one.
Sir,
okay. No, so I want you to have a go
at 45 degrees, sir.
I want you to have a go at this one. Okay.
So convert that 45, sir.
Yeah, so pardon?
That 45 degree. We don't have a variation over there.
I can't hear what you're saying.
That 45 degree, we don't have a variation over there.
You don't need a okay.
Okay, can you explain that one?
Okay, right, let's okay. So here's my compass. Yeah, a compass. So my aircraft compass is reading 045. Yep. My magnetic heading is 045. So if I take compass and magnetic away from each other, what's my deviation? 45 0. Take away 45 is
0.
0. Yeah.
Yeah.
Now, okay, here 45. So my magnetic heading is 45, 045. My true compass heading is 054. To go from 45 to
Positive, it means it is
Yeah,
going to east
45
9
to
degree.
54. When I find my pointer, must be
Point
plus
plus 9.
9,
Plus 9 to
and
east.
plus 9 must be
East.
east. Yeah.
Yeah, I got it, sir.
Again, and if I was going, just to highlight it, if I go, let's say I go this direction, because I can, 054, yeah, and it says 9 east, well, 9 east is positive. But if I now change that to, because I'm going to go from that way, 9 east becomes negative 9. 54 take away 9 gives me 45. Do you see that now?
Yeah.
Okay. So what I'd like you to do, gentlemen, is have a go at the third one. Okay, have a go at the third one. So this one here, one has got 1 each. So the third one down. And then have a go at the second one down. Okay? So have a go at the third one down, and then have a go at the second one down. Okay? I'll give you 5 or 10 minutes to have a go at that. Okay, I'll give you a few minutes anyway, and we'll go through it. And I think that will be it for today. So I think we're all tired.
Okay.
Yes?
You asking for second and third, right?
I can't hear what you said. Say that again.
Need to solve second and third.
Yeah. Go for that one and that one.
Okay. I think it is done. T.
It's done.
Okay, done.
It's okay.
Yeah. Yes.
Yeah. 29 in the upper one.
Yeah. I'll wait to make sure everyone else has a go. Okay.
Okay, sir.
Okay. If we all got an answer?
Yes. Yes.
Both? Okay. Who would like to do the one at the top for me, please? Anyone? Go on, somebody be brave and volunteer.
Yes. Yes.
Who's that?
Suresh.
Suresh, can you have a go then the top one, please?
Okay, we move from right to left.
Correct.
0116 degree.
Yep.
And the west is negative So when we move from the right to left, it has to be altered. Mine negative is positive. So the value is 0.27 degree magnetic. Okay.
Correct. That is correct.
Okay. There is a deviation of 2 degree west. West is negative, so we have to add again. So it compass course is 0.29 degree.
Spot on. Well done. Okay. Thank you. Anyone else want to have a go at the other one?
Then I will do it, sir.
Who's that?
Me, Naveen.
Okay, Naveen. Can you have a go then, please?
241, and then 8 east means it will be, we will have to subtract it, and 233 for magnetic.
Yep.
And then again plus 1 means 232 for compass course.
Okay. Did anyone else not get that? Did anyone else not get that? Good. Okay. Just want to highlight that one about 2142. For some reason, the west at that 5 degrees is missing. You can see there in the red. Can you just add that to your sheets? Okay. So if you get asked about calculating deviation or variation on magnetic heading or true heading, put up, write in your bit of, because you're going to get a bit of paper, write up Cadbury's Dairy Milk Very Tasty and just put the information straight underneath it, okay? And then you'll work out. Okay, gents, it's probably been a long week for you, okay? I have got to where I want to do today, okay? If you want to practice these over the weekend, please do, okay? I can't guarantee one of these will come up, but in a lot of the papers, one of these does tend to come up as a guaranteed mark. Let's put it that way. If you practice these, okay. Does anyone want to go over anything we have done today or yesterday? Okay, what I suggest you do, gentlemen, it's been a pleasure teaching you the last couple of days. What I suggest you do, I know it's night, it's what, nearly what? So it's six hours, so basically it's 9:30. So it's 9:15 in Kathmandu, is that right?
No, it's
9:15?
It's 9:10. It's
9:10.
Quarter to 9.
Right. I don't think you're going to be doing that tonight. Have a good rest, because you've probably had a hard week with Jim Campbell doing the other parts of Mod 11. What I suggest you do, if you want to, please read through your notes. If you have any questions and you don't want to forget, you've got I think you've got my email address, haven't you?
Yeah, Mr. Yadav, I think he has.
Right.
Mr.
Yeah,
Yadav will forward to us.
Yadav's definitely got my work's email address. Yadav, could you just put my work's email to everyone, my work's email address? So I'll probably look at my computer sometimes Sunday, and if there's any questions you have, if you email them, I'll have the answers ready for you on Monday morning. Okay? Are you happy with that?
Okay.
Yeah.
Okay.
Sure. Yeah.
So no one wants to go through anything again.
We'll take it on Monday once we go.
I think that's a good idea. So you gentlemen all get a good night's sleep. Okay?
Yeah.
Okay. Yes.
In our notes, we have this Weber's theory of ferromagnetism and some laws of magnetism. Do you need to require to study or not that?
Remember, I've been through them. Basically, laws of magnetism. Basically, they have a direct. So basically, go north south. They take the shortest route.
Okay.
They always either light poles attract, unlight poles. Light poles repel, unlight poles attract. That's the basic laws of magnetism. And what was the other question?
No.
Yes, Lynn, I have.
Yes.
So it's out of course question. You teach only this the B2 part, like instrument and electrical part, or you
Yeah,
have B1 part also you used to teach, or you teach?
I'll be teaching your avionics, lighting, and power parts of this module.
Okay, electrical as well.
Yes. Oh yeah.
Okay.
You've got me all the way through to next. So I've got you all next week and the first 2 days of the following week.
Okay, so in AST your part is only this electrical and instrument part.
Yeah,
not
I'm
the
the electrician. Okay.
Okay.
I don't do the mechanical bits.
Okay.
Okay. I just teach the avionic parts of module 11.
Thank you. Thank you.
Okay.
Yeah.
Right.
Okay, thank you. Happy
Have
weekend.
a good, gentlemen, have a good night's sleep. Have some rest. Drink a can of
And
Everest
happy
or
weekend.
Tusker beer.
You also enjoy your weekend, sir.
Okay, will do. So I will see you on Monday. Okay, but please have a read sometime in your notes, but please also have a good rest. Okay, you've worked hard. Have a rest. Okay.
Okay. Thank you. You too.
Okay. And I will see you on Monday.
Okay. See you.
Okay.
Bye-bye.
Bye.